Welcome to lecture 10, the last in the series. In this lecture, we are going to cover satellite network topic. That is how satellite can interconnect and transmit data between end-to-end users through multiple satellites or through some satellites and help of ground network. We will see also different topology architectures, and we will see different satellite constellation types. We'll see how do we formulate this constellation and how do we simulate them in using computer. I hope you'll enjoy this lecture. We studied so far the basic building block of a satellite network, which was a point-to-point connection. So in this case, we have a terminal A wants to talk to a terminal B or a hub or a ground station on the other side. Now, it is seldom that you just need to relay traffic between 2 points. Usually, you have a remote terminal wants to access the internet, and in this case, what you'll find that this is actually a gateway which is connected in turn to a larger network, for example, to the internet. Now, generally speaking, if we want to make a generic architecture of a satellite network, we'll have multiple satellites. These satellites are connected to different types of users. Users can either communicate through the satellite network, which we say this is a futuristic scenario. Today's most of satellite communication happening between the terminal. So the terminal talks to the satellite, and the satellite is connected to the internet. And then you can access any service you want through the internet. The question is, what is the difference between typical networks, the terrestrial networks we have, and satellite networks? Well, there are three, themes or domains where this difference can be seen. First is the mobility. Especially for low Earth orbit satellites, the satellites are always in relative movement with respect to the ground users. And that's a lot of things results from it. First of all, the topology, the interconnection between satellites will be different with time. There will be handover between satellites. So if you have a terminal, different satellites will pass at different time. You need to hand over your traffic. You can't have interruption. And also traffic demand will be different. So let's say you are a terminal above sea. There might be a few ships here, but as soon as you are above an urban area, there will be a lot of traffic generated from that urban area. The second domain is the limitation of the satellite itself. Now, the satellite is not connected to the mains power. It derives its power from solar arrays, from the sun, and it needs to store this energy in batteries and so on. So it has limited capacity in storing, limited capacity in interconnection, and also you need to optimize and troubleshoot. The satellite becomes much harder process to do because it's in space. You can't send someone to press a reset button. So when you develop something, it should be tested very, very well, and that sometimes create hurdles in time to market or in deploying the satellites because you want to test them very well. The third category is the nature of the constellation itself. So what we have here, we have a variable delay. Say you have a ground terminal. Now when the satellite is approaching, you'll find the delay is larger, then smaller, then again go larger. That means the delay itself is variable. There is a higher propagation delay when you deal with geostationary orbit. And we talked about that because geostationary orbits are located at 36,000 kilometers. However, the delay is much less when you are using LEO orbits. We'll show three example architectures with increasing complexity. In this example, we have multiple remote sites connected to a central hub. Now, you could do, as we saw previously, the assignment of resources based on FDMA or TDMA. These are the most common types of access method in satellite network, in such a simple satellite network. And let's say this is an example of a main office of a company, and you have remote sites in different locations. It also could be an example of an network operator, using a geostationary satellite where the hub is connected to the internet, and the sites, or here we call them users, are connected, the terminals are connected to end users. The second architecture example for broadband services for airborne users, that are the users on board airplanes. In this case, you have the airplanes are mobile users moving, for example, under a GEO satellite orbit. The GEO is connected to a hub. There is a network operation center, and this hub is connected to the internet. This is very similar to what we saw before, and it provides internet access for users on board the airplanes. Example 3 is different than 1 and 2 by it is much more complex. where we have the satellites could be interconnected. The services could be provided to airborne users, such as airplanes, could also provided to ship users, could be provided to remote mobile users, or to fixed users on the ground. So there's no here example, but then what we see this, you could have multiple hubs, multiple teleports, where they receive the signal for diversity as well as for providing global coverage. Now, when you see NOC, Network Operations Center, is usually our centers required for such large constellations. Now, we talked about low Earth orbit, that they have much lower latency than geo orbit because they are closer to the ground. We also talked about the possibility to provide inter-satellite connection, which reduces the end-to-end delay significantly when compared to optical fiber network. And we say the reason is the communication between two satellites is happening at the speed of light, while the communication between two ground terminals is happening at about 0.6 to 0.7 speed of light, because the propagation speed in fiber is slower than free space. Satellite constellations facilitate satellite networks, and they have multiple benefits. First, they can assure a global coverage by distributing the satellites around Earth. The second point is that you can increase the capacity and bandwidth by using a constellation. Let's take an example. For a LEO constellation, you can provide a small patch coverage, and you can reuse the assigned frequencies again and again for different satellites. And in this case, for example, you have 100 megahertz, you can provide 100 megabit per second for these users. For example, another 100 megabit per second for these users, and another 100 megabits per second for these users, and so on. However, so in total you will have 300. However, if you have a geo orbit, and then what you will find that this patch is very large, and instead of providing 300 or 600 megabits per second for the entire region, you are only providing 100. So there is an increase in the capacity and bandwidth because of the constellation use. The fourth item is the redundancy. In this example, we have a user, and this user having multiple visible satellites, so it can choose which one is providing higher bandwidth. Also, if one of them failed, you can still have others to utilize for redundancy. The fourth is inter-satellite networks, which we covered in previous slides. Two famous satellite constellations, one is called Walker Delta, the other is called Walker Star. And what you find here, and let's start with the basic orbit. So we have an inclined orbit here with a certain inclination. And what we do here, we copy paste that orbit and then rotate each copy around the z-axis of Earth. So you end up with a figure, something similar to what you see in the right-hand side. Now, in order to describe this constellation, you need actually five parameters basically, but there are three important parameters here. Traditionally, it's described in this three set. N is the total number of satellites in this constellation. The second parameter is the number of orbital planes. So you can see here, this is called an orbital plane, where multiple satellites are within an orbital plane. So the number of satellites per orbital plane will be number of satellites divided by the number of orbital planes. Let's say, as an example, we have 24 orbital planes, and each orbital plane will have 10 satellites. So we have the total number of satellites would be n. So that number of orbital planes would be p, and that would be n. This number 10 is actually the number of satellites per orbital plane, which is n divided by p. The third parameter is called phasing parameter, and that describes the so let us say this is your these are your satellites in a certain orbital plane. If I'm going to draw a next orbital plane, the satellites can be shifted. So the next orbital plane, the site does not have, can be you can push a bit of rotation for the satellites within the orbital plane. So in other words, this is, you are pushing the true anomaly by a certain phasing parameters. We call it f here. And as said, in order to describe an orbit, of course, you would need to know the inclination, and we need to know the height of that orbit. Typically, the orbits are with eccentricity of 0, so these are circular orbits. Now, the right ascension of the ascending node, which means when you rotate around the z-axis, it's part of this set. It means you start with a rotation of 0 to describe the first orbit, and let's say here's your first orbit, and then you shift by a quantity So let's say this is your first orbital plane, and then you shift. So here's the z-axis. You shift by an amount of 2 pi over p. P is the number of orbital plane, and so on. So the total orbital planes would be p. Walker star is quite similar to Walker delta, except that the orbits typically having very high inclination, that is, they are near polar orbits. You see these orbits here are near polar, means they're near passing to the pole. When you generate this constellation, so it's also described as n, p, f, which we already discussed these parameters. When you rotate the orbital plane, let's say I'm generating an orbital plane here, and I'm generating the next orbital plane, so you have to use this formula, which means you're distributing the orbital planes from 0. Instead of from 0 to 2 pi, you're generating them from 0 to pi. And the reason for that, best thing is when you generate the orbit, you will see that if you generate it from 0 to 2 pi, there will be an overlap in the generation. So remember, this orbit, what you'll find is some satellite will be ascending, and from the other side, the satellite will be descending. Random constellation is a theoretical constellations where it doesn't matter where is the inclination and the right ascension of the ascending node of the orbits. There is a certain way of generating them. If you're interested, you can refer to this paper. The benefit of such a random constellation, it allows you to derive very important mathematical expressions for the coverage and performance without relying on heavy simulations, and you can obtain insights between the different parameters in the constellation and the expected performance of the constellation based on these mathematical equations. We need first to create the parameters required to generate the Walker delta constellation. The first parameter is the radius of the orbit, and in this example I'm selecting a 1200 kilometer altitude. If I add 1200 kilometers to the Earth radius, that will give me the semi-major axis, or it will give me the radius. They are the same thing because I'm having an eccentricity of 0, means it's a circular orbit. I have selected an inclination of the orbits of 65 degrees, and then 12 orbital plane. This is the third parameter that I need to define. The fourth parameter is the total number of satellites, but instead of defining it directly, what I did here, I defined the number of satellites inside each plane, which is 24 in this example, and then the total number of satellites becomes 12 times 24. The second section, I'm going to make use of the built-in function within Matlab to create the Walker delta. So you can look at the Walker delta in Matlab help, how the syntax is being formulated, but basically we already defined all the parameters in the first section. So I ran this previously, and here is the resulting constellation. So as you can see here, we have a constellation which is Walker delta, and you can see that near to the pole at high latitude regions, there are no satellites covering the Earth poles. Alright, so let's have a look now on the Walker star constellation. Walker star, simply you replace the function of Walker delta with Walker star, but also remember that Walker star require higher inclination. So I'm going to use an example of 85 degrees, and I'm going to run this example. Let's see, the results will come shortly. This takes a bit of time because of creating all these satellites. Here is the satellites are coming, and now we can note shortly that these satellites are also passing very close to the poles, both the North Pole and the South Pole. So what you're seeing now is the Walker star constellation. There are different considerations when a satellites want to establish an inter-satellite connection with neighboring satellite. For example, you could have a limited number of lasers if this is using laser connection, such that you would prefer to connect with certain satellites rather than connecting with every visible satellite. And also, your satellite might have, the other satellite might be too far. As such, you cannot establish a laser link between your satellite and the far satellites. It might also be on the occluded or blocked by the curvature of Earth. So again, this doesn't have to be laser, could be a terahertz link or millimeter wave or a microwave link between the satellites. The first topology that we want to cover is the full mesh topology, where all the nodes, in this case the satellites, are interconnected directly together. For example, if satellite, let's give it a name A, wants to talk to satellite B, it can just utilize the connection that is established between A and B. There is no need to route the traffic through other satellites. From this perspective, this is much faster network. However, there is a drawback, of course. Now the drawback here, let's have an example. If you have a network with n number of satellites, the number of interconnection will grow exponentially with the number of satellites. So this is a combination problem. So you are picking up two connection or out of n. So that would be equal to n squared minus n divided by 2. So the total number of connections would be n squared minus n divided by 2. And each satellite would require an n minus 1 links. So these are total connections here. Total connections. And you need n minus 1 links for each satellite. So look at this, we have 5 nodes. Each satellite will require 4 connections to other satellites. So for a simple network, for example, let's say a 20 satellites, if you do the calculation here, you will find this will end up with a 190 total connection. And each satellite will require 19 ports, 19 different antenna to point at the other 19 satellites. Accordingly, a partial mesh topology balances the efficiency with practicality, because we saw that it's highly impractical to connect a large number of satellites, but also if you remove some of the connections, you will lose some of the efficiency. For example, if your satellite A wants to talk to satellite B, there is no direct link, so you reduce the efficiency here. In this case, you have to communicate through a third satellite or maybe through multiple other satellites. It depends on your routing algorithm and the weights and the different costs required to route your traffic. A hierarchical mesh technology or topology is a partial, of course, topology. What you can see here that each satellite group is served by a higher level satellite, and so on until you reach to the highest level satellites. Now this can be implemented in satellite application. For example, if you have a LEO network, so the LEO network does not have to be interconnected to each other. What you will have here, a MEO network. So the multiple LEO satellites will be connected to a single MEO satellite. And what you will find that multiple MEO satellites are connected to the GEO satellite. So this we call it a hierarchical mesh topology. For better efficiency, you can allow the interconnections between satellites at the same hierarchical layer. This is called, in this case, hybrid mesh topology. The satellite topology will have a tremendous effect on the delay and the variations of the delay between two ground terminals. So it's still an active area of research, and what we're showing you is some preliminary results on the comparison between two nodes connected by an optical fiber. So remember, if you connect two nodes by an optical fiber, the connection here is slower than the speed of light. However, if you connect it through a satellite network, yes, you will have some delay because of the distance, but the transmission per link will be fast. It will be actually appearing at the speed of light because it's in free space. We're going to explore two different topologies. The first, we call it the cutoff distance topology. In this topology, you have a certain distance. For example, for satellite B, there is a certain distance translated into a circle that any satellite within this circle can establish connection with B. So let's take an example. I'm going to put here a satellite E. So can E connect with B? Yes, it can, because it's within the circle. If, let's say I have a satellite F, and this satellite cannot connect with B because it is outside the connection circle, and so on. Now the question is, can E connect with F? Well, to answer that, I need to draw a circle around E, and I'm not sure if I will be successful in drawing a circle, but yeah, I have a circle. Yes, they are close enough, so I'm going to establish a connection between them. So in other words, this will the topology will depend on the limitation of your ISL technology, for example laser. So it will depend on the maximum distance that a laser can travel or can effectively establish a connection between two satellites. The second topology is a bit more complicated. I'm going to make a side drawing here. If you have 2 points, let's say a point A and a point C, now in order to establish a link, you should make sure that there is no other closer satellite between these two between these 2 points. So what you'll do here, you will draw a circle and say, okay, do I have any satellite within the circle? If there is no satellite between these between the A and C, then you can establish a connection. Now, if you find so you can establish a connection. I'm going to put it here. If you find another satellite, let's say satellite B, so then you cannot establish a connection between A and C. And then the question, can I establish a connection with between A and C? So the same scenario you will do here. You will draw a circle and see, is there any satellite between? There is no. So then you can draw this line, and then you establish another circle and ask this question, is there any satellite in this circle? There is no. And then as such, you establish another connection. So this is called the nearest hop, means you only establish a connection with your nearest point, that there is no other point nearer to your nearest neighbor. This is a preliminary result showing a connection between a point in Australia and one point in Europe. So this is a satellite network. We are just doing it in this case in 2D. And you can see there are two different routes basically. You have the nearest hop route, which is shown in red here, and you will have the cutoff route, which is shown in yellow. And then it's also comparing with the great circles. The great circle is an optical fiber, is an imaginary optical fiber connected between the 2 points. So this is not through the satellite. The green line is connected directly between the 2 communicating nodes. Now this section here and this section here is the connection between the network and the ground terminal. This is a 3D simulation of similar setup. We are simulating here the topology based on the cutoff distance. So we are connecting a point in Australia with another point, and we are routing our connection through the shortest path through the satellite network. And you can see as the simulation time progresses, this shortest path is not constant, it's keep changing. And that causes the delay itself to fluctuate. If you can look at the delay here, it's fluctuating as the satellite constellation progresses. This fluctuation is called the jitter, which is the changes or the variations in the delay, which is not something preferred in networks in general. So if you run the simulation for thousands of points distributed at different locations on Earth, and then obtain the average of the improvement. So what we are measuring here is the improvement in the latency when we compare the 2 points at two terminals connected by a great circle fiber versus connecting them by a satellite network. So the question here, do we get improvement? The answer, we do get improvement if the distance, so the x-axis showing the distance between the 2 points on the great circle, and the y-axis shows the improvement that you might get. So if the points on Earth, if 2 terminals are separated by 4,000 kilometers and more, you will find that the delay in optical fiber networks and satellite networks is almost identical. But as the distance increases between the points, you'll find there is a significant improvement in the delay, means the delay if you route your traffic through a satellite network will be, for example, at this point will be 20% faster than if you route it through a great circle fiber. Now mind, these are initial studies and these are theoretical studies as such, because you don't have a fiber connected between 2 points, but this explore the possibilities. What is the maximum possibility of delay saving that we can do if we used a mega satellite constellation? This is the end of lecture 10, which brings us to the conclusion of this course. I hope it was beneficial and enjoyable to you. I also wanted to take the chance and wish you all the best in your studies.